What up? It's 1:06 p.m., so you know what time it is. It's problem of the day time. Today we've got minimum number of removals to make mountain array. It gives us the definition of a mountain array, which is that it must have a length greater than or equal to 3, and it must have a peak where each number before the peak forms an increasing subsequence, and each number after the peak forms a decreasing sequence. And it tells us this peak must be strictly greater than 0 and strictly less than the length of the array minus 1. It asks us to find the minimum number of elements to remove to make nums a mountain array. One thing that's really useful could be to consider the complement, right? So I have a minimization problem that says minimum number of removals to make mountain array. I might think about what could I maximize to solve the same problem. And so in this case, we might want to maximize the size of a mountain array that we can form from removing elements from the original array. By maximizing the remaining mountain array, we minimize removals. So if I think about it in terms of that, what's the largest mountain array I can form? I can ask myself other questions about the problem. I could break it into subproblems. I could say, hey, let me consider each peak, each possible peak, like this one or this one or this one, and consider how many removals I might need to do to actually form a mountain array, and then choose the one which results in the minimum number of removals. But how do we approach actually forming the mountain array? Well, if we look back at our definition, we notice that it says that the elements up to the peak must be strictly increasing, and elements after must be strictly decreasing. This in and of itself is a problem. We can say, how can I form a increasing subsequence which is as long as possible to maximize the length of my mountain array? Luckily, Leetcode actually has this problem as its own sort of link that we can look at. And so we can solve this subproblem of the longest increasing subsequence and then come back here to solve the minimum removals to make mountain array. So let's check out longest increasing subsequence. This problem is a bit easier. It just says, given an integer array nums, return the length of the longest strictly increasing subsequence. First of all, let's just think about, can we brute force this? How many subsequences of the list of numbers are there? If there are n numbers, we can include or not include each number, which means we have two options for including or not including it for each of n numbers. So there are 2 to the n possible subsequences. If we look at our constraints, we see that the length of the list could be up to 2,500. How big is 2 to the 2,500? Way too big for us to ever finish in time. Usually we want something that's on the order of 10 to the 8 or less. So we need to think about how to make an optimization. How can we do something that's faster than a brute force? Again, we could think about, hey, can we break this into subproblems? Let's make a drawing, and it might be easier. Let's have this be our hypothetical array. And let's draw a longest increasing subsequence for it. So maybe we skip some elements and connect others to form the longest possible increasing subsequence. So we would imagine that there are elements at various positions in our array, but we skip some of them maybe because they wouldn't form an increasing subsequence or because there are better numbers to choose. But these specific numbers form the longest subsequence that's increasing that we possibly could have. Let's see if we can find any structure in this that we could take advantage of. One way that I always like to try and think about is if we can just break off a single step and notice anything about that step. So for example, this is the last step in our subsequence. So let's look at this position right here. Is there anything we could say about the remaining subsequence, which has to be true for the whole subsequence to be the longest increasing subsequence? There is. What we can say about this subsequence is that it has to be the longest increasing subsequence which ends at this position in the whole array. And the reason this is true is because if it wasn't, we could replace it with the longest increasing subsequence which ends at this position, so one that's longer than this one, and increase the length of our overall subsequence up to here. That would be a contradiction because we assumed outright in the beginning, in the first place, that this was the longest one possible. So for that not to be broken, this has to be the longest one possible ending here. So if you notice, this is actually saying that the longest increasing subsequence is formed out of other longest increasing subsequences. This property is called optimal substructure. And it means we can take advantage of something called dynamic programming to make it so we don't have to do exponentially many comparisons. And typically dynamic programming just means that we're going to cache or save answers. So in this case, we might ask, well, what are we going to save? Well, it's sort of indicated to us right here that what we care about is the longest increasing subsequence ending at a position. So we can use positions or indexes to parameterize or enumerate all of our longest increasing subsequences. And because we found that each subsequence of a high index is formed out of ones from previous indices, we can use those to form solutions for every index. And once we have a solution for every index, we have a solution for the whole array, because we could just take the maximum out of all of them. So let's write this recurrence a bit more explicitly. What is this relationship? Well, whenever we're considering a specific index, like I, we want to look at every j, so every index j that comes before I. And we want to look at the longest increasing subsequence that ends at j. And if that sequence ends with a number which is less than the number at I, then it's up for consideration. We'll take the maximum out of all of those such sequences. And then whichever one is the maximum, let's say this position right here had the longest increasing subsequence, and it had a number less than this number, then we could add that one last step to form the longest increasing subsequence ending at I. In this case, the longest increasing subsequence which ends at a position before I and has a number which is less than I is actually right here from our drawing, right? And we connect it with this last step. And similarly, for this position, it's this one, and we connect it with this last step. So if I were to write down what this recurrence is, we would say LIS, that's short for longest increasing subsequence, of I is equal to 1, so that last step, plus the max of LIS, so this is where that substructure comes in. We have a recursive relationship here of j. And we want to consider each j which comes before I, and only those which end with a number j which is less than the number at I. Bam. So let's implement this to solve our longest increasing subsequence problem. I'm going to make a table called LIS, which has all of the lengths of the longest increasing subsequences for each index. I'm going to start each value with the number 1, because we can always just have the number itself as a subsequence, valid increasing subsequence. And I'm going to iterate over each I in the length of the array. And I'm going to use our recurrence to fill in the values of our table. So I would say for each j less than I, if the number at j is less than the number at I, then I want to make sure that the number at I is updated to be the maximum possible. So it'll either be its current value or the value of our recurrence, which was 1 plus LIS of j. Once we've done all this iteration, our table will be full, and we can just return the maximum out of all of our options. I think this should be sufficient. Let's see. Ooh. Oh, there's a typo. Bam. And let's submit. Nice. Accepted. So you might notice if you look at this distribution, we're in this sort of low time bump, and then there's a much faster bump up here. So we might ask ourselves, can we do better? First thing to look at when we're trying to see if we can do better is, what is our time complexity? Well, if there are n items, we're iterating through n items right here, each index in nums, and then for each index in nums, we're iterating through all the indices less than it. So essentially, we're adding up 1 plus 2 plus 3 plus 4, so on, all the way up to n. And this is going to be quadratic, right? This is going to look like something like this, according to Gauss or whatever, right? We're going to have n times n as the largest term, which means we have an order n square time complexity. Can we do better? Yes, we can, but we're going to have to go all the way back to 1961 and look at Schensted to find out. So let's take a little detour. So this paper is called Longest Increasing and Decreasing Subsequences. It was written by Schensted and published in 1961. I highlighted some things here for us to look at because it'll help us find a faster solution for our longest increasing subsequence. So the first thing to look at here is just, what is a Young tableau? It's a structure we're going to be looking at and studying to help us form longest increasing subsequences. And basically, it's just a grid of squares filled with numbers, right? So you can have a number of rows and a number of columns, and each of the rows are going to need to be increasing in terms of the numbers that are in them, and each of the columns are going to need to be increasing in terms of the numbers that are in them. And it's going to have to be left justified, meaning that each row has element from the first column, and each column has an element from the first row. So like if you look at this little image right here, we have 2, 4, 7, 3, 8, 5, 9. Those are increasing rows. 2, 3, 5, 4, 8, 9, 7, increasing columns. And you see it's sort of justified. If we took these 4 numbers and shifted them over so that there was space under the 2, it would no longer be a Young tableau. They're often written with these squares. Why do we care about Young tableaus? We care about them because you might notice this increasing property is relevant to our problem. So let's keep reading. Here it tells us that there's a definition Sx, which is defined as an array obtained from the standard tableau S by means of the following steps. These steps that are being described are something called Schensted's algorithm. What they allow you to do is to take a sequence of numbers and form a standard Young tableau out of them. So essentially, if I have a number and I want to insert into my standard table, I will put X in the smallest place I can without breaking the increasing row rule. And if I can't, and if there's a number in that position, so if there's not a number in that position, so if it's the last position in the row, I'll just add it and I'm done. If there's a position in its place, I will do the same thing until I either find a suitable place or I form a new row. I actually found this website. It's called integraldomain.org. It allows us to visualize it, right? So if I have an empty Young tableau and I add 1, and then 2, then 3, then 4, then 5, then 6, since these are in increasing order, we're always just going to add to the end of the row. Kind of trivial. But if we do it in a more unordered way, unordered permutation, so let's try like 1, 4, 2, let's predict what's going to happen, right? The latest place that we can put it without it, if we put it at the end here, it'll go 1, 4, 2, and it won't be increasing. So the latest place we could put it is where the 4 is. And so the 4 will get bumped down. Let's see if that's what happens. Bam. Right? 1, 2, 4. How about 3? Well, 3 is greater than 2, so we can just put it at the end. Yep. Same with 6. How about 5? Well, I can't add a 5 to the end because it'll break the increasing row rule. But I can put it where the 6 is. So now I put the 6 in the latest position I can, which is after the 4. And we're done. Let's try one more example, right? We could do 1, 5, 6, 4, 3, 2. This one had to do a whole lot of bumps, right? One thing you might have noticed when I was doing all of these is that this sequence seems suspiciously equal in length to the longest increasing subsequence. And we'll soon see that that's actually provably true. Need to do a little bit more reading first. So by the way, again, that's called Schensted's algorithm. So this goes into naming things a bit. It talks about the P symbol and the Q symbol. P symbol essentially says if we have arbitrary numbers, like in our Leetcode problem, and we form a table out of them using Schensted's algorithm, we name it a P symbol. Versus if we only did it for the first n natural numbers, like in our little animation here, then we would call it the Q symbol. And the utility of having the Q symbol is that it's a bit easier to talk about correspondences and stuff. So if you want to learn more about, I think there's something called the Schensted Correspondence, which maps these tableaus to permutations of the first n integers. Check this paper out. But it's not as relevant to us. What we care about are these lemmas. So what it talks about is, it says the jth basic subsequence of a given sequence consists of the digits which are inserted into the jth place in the first row of the P symbol. That was a lot. What does that mean? Let's go back to our animation again, right? What it means is that if I have a table and I'm inserting numbers into the sequence using Schensted's algorithm, if I take a position in my row, first row, let's look at the second position right here. The numbers which occupy it throughout the insertions form a basic sequence. They form the second basic sequence. So for example, right now the first element of the second basic sequence would be 4. If I would put a 3, the 4 gets replaced, and now the second element of the first row is 3. So the second element of the basic sequence is 3. And if I put a 2, same thing happens. 5 and 6, they don't touch this. So our basic sequence for this insertion order was 4, 3, 2. You could think something similarly. The insertion sequence, the basic sequence for this was 1 for the first position. It'll always be 1 for the first position. For the third, it was just 5, and for the fourth, it was just 6. He outlines these two lemmas and shows that this theorem, the number of columns in the P symbol, which is the same as the length of our top row, is equal to the length of the longest increasing subsequence of the corresponding sequence. So if we can prove this, what we just learned from here, if we can follow this proof, is that by following Schensted's algorithm, we can obtain the length of the longest increasing subsequence just by looking at the top row of this tableau formed using Schensted's algorithm. So let's see if we can understand this proof a bit better. Lemma 4 just says each basic subsequence is a decreasing subsequence. You might have noticed that, right? Here we had 4, 3, 2. To prove this, he just says that if we look at what Shensted's algorithm is actually doing, right, it's putting the number in the earliest possible place and moving larger numbers down, right? If the sequence were to not decrease, so if it were to increase, then we would be performing the algorithm wrong, right? Like if I have 1, 2, 3, and I replace the 3 with a 4, well, I should have put the 4 next to the 3. He says something similar here. Each number in the jth basic subsequence on insertion in the first row displaces the previous member of the jth basic subsequence, which must therefore be larger than the present number. And it has to be because that was the definition of our Schensted insertion. And so the only other thing we need to know is lemma 5. It says, given any member of the jth basic subsequence, we can find a member of the j minus first basic subsequence, which is smaller and which occurs further to the left in the given sequence. So basically he's saying for any column here, we can find in the previous column a number which is both smaller and earlier in terms of the numbers that we're inserting. And this sort of has to be true just by the definition of the Young tableau, right? If we couldn't, that would either mean that the row wasn't increasing or that the number that came before comes after the number that we're currently considering in the sequence of insertions. And neither of those actually adhere to the Schensted insertion construction that we made, right? So we look at the proof, it's also pretty short. It says the number in the j minus first place in the first row is such a member. It basically just says this is true by definition. And so lastly, we can just compose both of these to get our theorem. We say the number of columns is the same as the number of basic subsequences. Trivially true, right? Number of columns is the same as the number of positions in the first row, because the first row is the largest row. And so by lemma 4, there can be at most one member of each basic subsequence in any increasing subsequence. So that is to say, only one number from each of those sequences we talked about, so 1, 4, 3, 2, 5, and 6, can actually be in this top row, because if it wasn't, then it would break the definition of basic subsequence that we upheld. So then lastly, it says lemma 5, we can construct an increasing subsequence with one element from each basic subsequence. With one element from each basic subsequence, we can form a longest increasing subsequence, and it corresponds to this top row, which is the longest out of all the rows in our Young tableau by definition. If it's not obvious why this is like maximal or why it's unique, I'd implore you to look into what I talked about earlier, the Schensted Correspondence, because it makes a one-to-one relationship from these sequences of insertions to these Young tableaus. But so what's important for us to take away from this is that if we can perform this insertion, which is to always sort of just greedily put it in the earliest position we possibly can, we can get the length of our longest increasing subsequence without having to iterate through every previous index. We can actually find this index that we need to insert it at, right? So like, let's say we have 1, 5, and we need to say, hey, where are we going to put in 4? We don't actually need to look at every index. We can, because this row is always in increasing order by definition, we can use binary search. So let's do that. Over here, I'm going to make our empty top row, and I'm going to iterate through each number and insert it in the top row according to our Schensted insertion. And as for how to actually find the index to insert it, Python has a built-in binary search we can use. It's called bisect left. Locate the insertion point for x in A to maintain sorted order. So let's just say bisect left, nums, num. And what did our Schensted insertion say to do? It said that if I was equal to the length of the array, we should just append it. Not the array, the row. We should just append it to the row. Otherwise, we should replace the number that's currently there and push the other number down. But if we remember from our theorem, we really only care about the length of this top row. So instead of pushing these numbers down, I'm just going to discard them. We basically never look at them again. So I'm going to replace that position with a number, and whatever was at this position I don't care about anymore. And once I've inserted all my numbers, I can just take the length of our top row and return that. Had a typo there. Should be looking at the top row. There we go. And if I submit this, we'll see that this actually falls into the higher performant bump in the distribution here. And again, let's look at time complexity. Is there like a substantial reason why this is faster versus it just being like a hardware optimization or something? We iterate through each number again, so this is n iterations. But because we only do a binary search and then operations which don't depend on the length of nums, this is only log n. So we have n log n time complexity. That's a big improvement. Finally, let's use this to solve our minimum number of removals to make mountain array. We just need to look at each peak. So we break it into subproblems and ask, what's the longest increasing subsequence which ends at this peak, and then the longest decreasing subsequence which starts at this peak. And if you notice, we could just iterate in the opposite order and it would be increasing subsequence, right? Like if I look at these numbers right here and I go from right to left, then all of these greater thans I could think of as less thans. So honestly, let's just copy and paste this and do it for each peak, right? I'm going to say longest ending at equals 1 times length of nums. And to fill that up, I'm going to use this. There is one thing we need to be careful of though, which is that when we did this greedily, we didn't care which number the sequence ended with. But in this case, because we're considering it for every peak, we care that it ends with exactly the peak. So instead of taking the length of the row, we're going to have to look at the index of insertion, because we know for sure that the number that we just inserted will be at that index, right? So it'll be clear when I implement it here. We have our top row. We're going to say for num and nums. Actually, what I'm going to do is I'm going to say for peak and num, enumerate nums, so that I have the position as well. I'm still going to find the position of the number in our row, and I'm still going to do this insertion. I'm going to make sure I save what this insertion was. So let's rename it a little bit more aptly so it's easier to understand. Basically, we know that the longest increasing subsequence, which ends with this number, will have a position, which is where we inserted at. So this is the number we want to save. The longest ending at peak equals longest. And we can do the same thing for our decreasing subsequences, which start at a number. So let's copy paste this whole snippet and replace this ending with a starting. Put this here, and then make sure that we do this in reverse order. Let's print both of them and sort of do like a sanity check, right? Do these values match our expectations? And let's return just 0 so that Leetcode doesn't get mad at us. So if we look here, numbers seem 1 too small. Oh, I'm still thinking in math brain, I think. It's 0 indexed, so this should be longest plus 1. This looks correct. Longest increasing subsequence at position 0 is just 1, then 1, 3, then just 1 again. Same for the other direction, because this array is symmetrical. If we look at this one, we have longest increasing subsequence would just be 2, then just 1, then just 1, then 1, 5 or 2, 5, so 2, then 1, 5, 6 or 2, 5, 6, so 3. And we see that's right in the other direction as well, right? We have 1, 1, 1, 3, 1, 2, 1, 2, 2, 1, 2, 6, 3, and so on. I'm not going to keep going. We have the longest increasing subsequence, which ends at each position, and the longest decreasing subsequence, which starts at each position. We can use this to form our longest possible mountain array and use that to find the minimum number of removals. So let's do it, right? We're going to say our candidate mountain lengths. Actually, let's just call it mountain lengths, right? It's going to equal, so actually I'm going to make this a little bit easier. Longest ending at equals L, and longest starting at equals R. And this is just to make it easier for us, right? This is our left side, this is our right side of the mountain. If I were to draw it, right, it's like we have our longest increasing subsequence at a position right here, longest decreasing. This is our left side, this is our right side. We have our longest, our left and our right, and for our mountain lengths, we're gonna add the left of a peak plus the right of a peak. And one thing we need to make sure of is not to overcount, right? If you think about it, like 1, 5 right here is why this is 2, includes the peak. And 3 for 1, 2, 5 includes 5 for this number. If we just added them together, we'd count the 5 twice. So let's make sure to subtract 1 for the peak. And also, let's make sure we don't forget our definition. So we have for peak in range has to be strictly greater than 0 and less than length of nums minus 1. So 1, length of nums minus 1. And this length has to actually exceed 3. But before that, there's one more thing we need to notice as well, which is that because this index is strictly greater than 0, if one of our subsequences was composed of only one number, it actually can't work, right? So like for example, we can't actually have a mountain array which starts here. Why not? Because there has to be an increasing and a decreasing subsequence. It can't just be that both sides are the increasing and decreasing subsequences. Notice that it requires both. So what we have to do here is we actually have to say that L of peak has to be greater than or equal to 2. So basically no single number subsequences. And you'll notice that implicitly this already satisfies length greater than or equal to 3, right? If the left has to be at least 2, right has to be at least 2, then they're both at least 2. And together are greater than 3 because they're 4, right? One last thing, I'm going to make this a generator so that I'm not wasting space. And so then we'll take the length of our nums and subtract the max mountain length. And see how this goes. Nice. And let's submit. Accepted, and we're pretty high up there in terms of performance. If you think about what is our time complexity, if we remember from longest increasing subsequence, each of these was n log n. Doing n log n twice is still just n log n. And then all of this, we only iterated through n items and did constant time operations. So we're adding linear time. So overall, this is still just an nlgn algorithm. Welcome to Jaden. Thank you for watching. I post solutions in my Discord, so if you want to join, I have the link down below. And comment below on other walkthroughs you might want to see.